All right, so this is 13.1. This is the beginning of chapter 13, and that chapter 13 in general is sort of basically a look at functions of several variables and partial derivatives and some applications of those. And so 13.1, I'm actually going to divide into two sections just because it makes it a little more palatable. So we'll call it 13.1A, and this will just be functions and equations with several variables. And so what we'll do is give some examples, give some definitions rather, give some examples, and that's about it. And then in 13.B we'll talk about level curves, level surfaces, which they kind of go together, but it's best to keep them separate. So just by way of little recall, and this is stuff that you know, but just so we have a context, is that we know that every function, just in a regular calculus sense, every function is an equation, but not every equation is a function. So they, they both turn up and they're both useful, right? So every function is an equation, but not every equation is a function. Again, this is in the standard sort of pre-calculus calculus way. So for example, a function like f of x equals x squared, right? This is identical. Like another way to write this would be y equals x squared. Right? That's also an equation, right? You could manipulate it. You don't have to, but you could, for example, subtract the y and get this. These are all equivalent. Right? So it's a function here, and we think of it as an equation in these two. Whereas something like a circle, x squared plus y squared equals 9, this is not a function, right? This is an equation. If you try and solve it for y, for example, you have to make a choice, plus or minus. And that plus or minus fails the vertical line test. Not a function. So we're going to have the same sort of behavior when we talk about functions of more than one variable and equations of more than two variables, right? So in our case, the case that we just saw, the functions are functions of one variable. The equations are equations of two variables. So we need to bump these up a few dimensions. And now, just to be clear, we've already seen some equations in this course. Equation of a sphere, equation of a plane. We've seen those. So we just need to round that out a bit more and look at a few more examples. So a function of, let's say, more than one variable. I'm saying definition, but this is more of a notation because it's fairly clear what the definition is from the notation. Is denoted, for example, something like f of xy. I'll just do a few examples here. I'm not going to sketch anything just yet. Let's just get the notation down. Could be like x squared plus y squared. Or f of xy could be, say, x squared y plus sine of x. Doesn't have to be anything nice. Nothing like that. In place of f of xy, we could go to the next variable in the alphabet and do like z equals, say, x minus y. This is the same as, it's treated basically the same as f of xy equals x minus y. Another one would be something like f of xy equals x over y, etc. And so, definition. This is not really a definition either, but so back here we had a function of more than one variable. And the ones I did here were both two, but let me just chuck another one down here. It doesn't have to be two. You could have as many variables as you want. We'll generally stick with two, because that's as far as we need to go, but something like x squared y minus e to z. Perfectly good function of three variables. Now, definition is, actually let me delete the word definition. It's not really accurate there. So let me say similarly to this comment right here. every function, let's be very specific here, every function in 2 variables is an equation in 3 variables. So for example, something like a function like f of xy is x squared minus y plus 1. This is the same as z equals x squared minus y plus 1, which is then an equation, right? And again, you can manipulate it, you don't have to, but just for the sake of argument, you could maybe move the z over. But the point is, you can see in both of these cases, this is an equation in 3 variables because you pick up the extra z there. Now, of course, not every equation in 3 variables is a function in 2 variables. Let's say the reverse, however, the reverse is not true. And we've seen one already. For example, a sphere. A nice simple sphere centered at the origin. Something like this, sphere of radius 9 or radius 3. Right. If you were to try and solve, say, for z, right, you have to make a choice. So again, this is not a function. So we have a lot of the same patterns emerging, right? Like you can have functions of 2 variables, which are equations in 3 variables. And likewise, you can have functions in 3 variables, which are equations in 4 variables, right? So likewise, and we won't generally go this high in dimensions. Likewise, a function in 3 variables is an equation in 4. So for example, say f of xyz equals x plus yz. You'd need a different letter for the f of xy, z. Say w could be traditional, but the letter really doesn't matter. The point is that we get an equation that involves 4 variables. So again, the big thing to remember is every function is an equation, but not every equation is a function. And just this notation that we write something like f of x comma y or f of x comma y comma z doesn't have to be x and y. It could be f of a comma b. They're just variables. Doesn't matter. So next what we want to do is really just look at a bunch of examples. We want to build like a library in our heads of examples of functions of several variables. What do they look like? How can we use them? Etc. etc. So let me clear the screen and I'll just sort of charge through a few, and I'll start with a really basic one so we know really what we're drawing when we talk about the graph of a function of 2 variables, and then we'll go from there. So let's say 3 examples. And for a lot of these examples, there'll be sort of 2-dimensional analogs that can really help you see what's going on. But before worrying about that, let's just look at a really simple example like f of xy equals x squared plus y squared. This is a great example to start with, right? So we could think of this as z equals x squared plus y squared. Now, what you could do is you could plot a lot of points, right? So we could plot points. We won't really, but I will list a few points just so that we see. So I would plug in x and y, and I would get out a z. So just to sort of see what's going on, if you plug in, say, 0, 0, you get 0. If you plug in, say, 1, 0, you get 1. 0, 1, you get 1. What you start to see happening, though, like if you plug in 1 and 1, you get 2. If you plug in, say, 1 and 2, you get 5. So as x and y, actually, let me do one more. If you plug in, say, -1 and -2, you still get 5. So the point is, in this case specifically, as these get further from 0, 0, let's say as these leave 0, 0, this value gets larger. And it'll get larger faster and faster because of the squares, right? So if you plug in, say, 2 and 2, you get 8. If you plug in 3 and 3, you get 18, right? So what happens is we get the following. if you were to plot all these, so we'll go back to sort of the beginning of the course, we'll draw an axis. And so we have the point 0, 0. Again, I'm not going to plot all the points, but that's right there at the origin. And as we move away from that in the x and y sense, we go up. And so what we get is we get a picture that looks like this. It looks like a, kind of like a, has a name, which I'll give you in a second. It looks sort of like a three-dimensional parabola. Right? So this is what's called a paraboloid. This is a shape we'll draw a lot over the course. This will become an old friend. Right? And something to keep in mind is this paraboloid doesn't stop somewhere at the top. It goes up and up forever. But that's sort of hard to draw, so we sort of stop it somewhere. But keep in mind that it goes up forever. And so if you wanted like a nice three-dimensional picture, you could sort of draw something fancy. You could, you could make the axes sort of hide. Like, again, the pictures don't need to be beautiful. They just need to be adequate. They need to get the point across. Something like that might be like a really nice picture. But the idea is to get the feeling of this thing. It's kind of like a ball, but it goes exponential the higher you get. So let me do a few more based upon that theme. So what if we did something like f of xy equals, do a very simple change, and say 1 plus x squared plus y squared. So what happens is, in this case, if we think of this, 1, this is a shift up. This is a familiar behavior because we're adding 1 to all of the z's. So it's essentially the same picture. But the whole picture is shifted up by 1. It's the same shape, basically, but it's shifted up by 1 unit. So that bottom is at z equals 1. Now, while we're at it, let me sort of add a little comment to these. The first of these, you could think of it as like a three-dimensional version of, this is similar to y equals x squared. You could think of it like a three-dimensional version of that. And this one right here, this is similar to, say, y equals x squared plus 1, or 1 plus x squared, for example. So those are familiar things that can help you keep in mind what's going on in this case. So let me do 2 more. So we'll do, and this one I'll put z. Again, same as doing f of xy. Doesn't really matter, won't change anything in that sense. So I'll do, say, 4 minus x squared minus y squared. So this is the same as z equals 4 minus parentheses x squared plus y squared. So this is a paraboloid that opens down, but it's been shifted up. So the minus makes it open down. So the 4 is a shift up, and the minus sort of flips it, if you prefer. So what happens is the picture we get starts up at 4, opens down. Now it doesn't stop at the xy plane, keeps going. I'm going to stop it there just because it makes the picture pretty. And then I'll do one more, just to sort of confuse and disorient you, because it's good for us. Right? So what I'm going to do is I'm going to switch some of the variables around. So look at something like, say, y equals x squared plus z squared. So what I've done here is I've switched the y and the z. So what happens is the old version, and so compare this one, oops, I'm not changing the axes though. Like the original one, the one way back at the beginning, this guy right here. Or, you could look at it this way if you like. That one, it wraps around the z-axis, right? Down in that first picture that we drew, it opens up and sort of contains the z-axis. This one, the letters are just switched around. So this one will open up and contain the y-axis. So this looks like this. Now, something to note, you might say like, well, is this a function? So it's a bit of a sloppy picture, right? So the answer is like, it's not a function in the sense that you can't solve for z and get a unique value. But you could argue that y is a function of x and y, or of x and z. Now, we're not going to spend too much time obsessing over what's a function of what, but just if it's interesting to you, that's something to keep in mind. You could think of this as like f of xz equals x squared plus z squared. You could argue that y is a function of z. Nothing wrong with that argument. Now, if we said something like, is this a function? You'd have to sort of clarify exactly what you mean. But that's okay. Now, all of these, though, these are all paraboloids. Again, like I said, these will become very, very familiar to us. But these are just a few basic examples. So I'm going to clear the screen and draw some more. One thing I want you to do, though, as you're studying this is think of variations on this, right? Like, what if you had switched if you had the x equals y squared plus z squared? What if you added a number? What if what if you wanted to shift it down and have it open up, or have it shift to the right and open left? So think of variations on a theme. Think of like different possibilities you could have. So what I'll do next is I'm going to do one that looks very similar to this, or that the equation looks very similar, but the picture is quite different. So sort of put this in your head, and let me clear the screen and do a different one. So for this one, take a look at f of xy equals, say, square root of x squared plus y squared. The only thing that changed is I put a square root in there. So one way to look at this and to think about what it looks like is let's hunt down the two-dimensional analogy for this. Instead of plotting points, you can plot points, but it's actually not very enlightening here. But the two-dimensional version, if you like, you might see it, or you might guess it's something like square root of x squared. Now, you might suggest that the square root of x squared is x, but it isn't. Right? The square root of x squared is the absolute value of x. For example, the square root of -3 squared is the square root of 9, which is 3. Right? So this is equivalent to y equals the absolute value of x, which we know what that looks like. So when we bump this up into 3D, our f of xy turns out to be the three-dimensional version of this as a cone. So this cone opens up at a 45-degree angle. I tend to draw these things too narrow. Like that. This is 45 degrees in here. It's 45 degrees inside as well. And again, goes up and up and up forever. So that square root, like, it's still a thing that opens up, but it opens up in a very different way because of that square root. And likewise, we can, let me label this before we move on. This is a cone. So let me do a few variations on this, right? So all of the next few will be cone related. And I say cone related because there's one example I'm going to do which is a little bit sneaky. But at least the next couple will be cones. So if we did say like 9 minus square root of x squared plus y squared, this is shifted up, but opening down. Just like we did with the paraboloid. So the vertex, if you like, for this cone is up at 9. Comes down, hits the xy plane. Does keep going forever. Again, I'm stopping at the xy plane because it makes a pretty picture, but it goes forever and ever on down like that. I'll do 2 more. Oops, didn't want to do that. Wanted to do that in black. So let me do, for this one, let's do something like, actually let me do 3 more. I'll do one that opens up. So we could do like -3 plus the square root of x squared plus y squared. This one is shifted down because of the -3. but opens up because of the plus square root. So this one looks something like that. And I'll keep this going beyond the xy plane, just so we have a more complete picture. It cuts through the xy plane in a circle. This is down at -3. And this goes up and up and up forever as well. All right, two more. So one is, instead of writing f of xy, I'll write z, but I'll write something like x equals the square root of y squared plus z squared. So what I've done here, compared to the first one, the very first one, is I've reversed, interchanged the z and the x. So what happens here is this opens up around the x-axis. This is actually pretty challenging to draw. So there's like a circle around the x-axis, and it goes like this. It's a tricky picture. I'll tend to not ask for things like this that are too hard to draw, but this is kind of okay. But this comes forward. Again, forever and ever and ever. And then one last one, just to make an interesting point. I'm going to write down an equation in 3 variables, like this. Right? So this equation is not a function, because if you try and solve for z, or for anything in fact, you end up getting plus or minuses. But this is the same as z equals plus or minus square root of x squared plus y squared. And this is actually 2 cones. Right? The plus is a cone that opens up, like this, and the minus is a cone that opens down. So what we get here is what's typically known as a double cone. Although sometimes the book, for example, will just say cone, but they mean double cone. It's sort of a bit sloppy, but so this thing, it's like join 2 cones. It's a terrible way to order ice cream. Now, so again, the plus one is the plus version up here. This is z equals plus square root of x squared plus y squared. This is z equals negative square root of x squared plus y squared. Now, just so that you know, there are some terms that show up in the textbook that you might want to know that come from this. There's some historical names. This top part is called the upper nap, and this one is called the lower nap. I will tend to not use those terms, but the book does use them, so keep them in mind. It could say something like something about the upper nap of the cone or the lower nap of the double cone or something like that. So just be aware, those are just different terms that are used. But again, everything you see in this page is basically a cone, except for that double cone, which is kind of 2 cones put together. So again, I'm going to do one more that again will look like these. The first 2 that we did equation-wise. And I'm doing these first so that you get to compare and contrast them. Or just compare them, really, is grammatically correct. And then we'll just sort of throw out a few more esoteric examples. But, you know, but the ones that we're building here are like the really fundamental ones that students get confused because the equations are very similar. Let me clear the screen off, do one last batch before we do a big collection. So what I want to do is come back and I want to do another one involving a square root. But now there's a constant inside it. Now you might be tempted to believe this is a cone as well, but it isn't. And that's not at all obvious why, except when we start to manipulate, right? So you might say, is it a cone? Now, the 2D version of this, you might think it up, you might be like, well, it's something like this. And this, you may know, is the top half of a sphere, because of a circle rather. Because if we start manipulating this, this guy is a full circle. I'm going to keep saying sphere accidentally. This is a full circle. This is the top half. So likewise, if I take this original equation, the one at the very top, or original function, if you like, and we manipulate it, this is a sphere. The equation we started with, this one, this is the top half of that sphere. If you were to solve for z and get the plus version, this is a hemisphere. So this one this looks a bit like a paraboloid, but it isn't a paraboloid. This does actually stop at the xy plane. Like it literally stops there. Stops at the xy plane. It's a hemisphere of radius 3 because of that line right there. So this will go to 3, to 3, to negative 3. You don't have to label everything. To negative 3 at the back and to 3 on the z-axis. So hemispheres, the equations look very similar to cones, especially because of the square root, but parabolas also because of the x squared and the y squared, but they're different. Right? So here's one more hemisphere. I'm just going to sort of mix the variables up a bit. So we could do like y equals the square root of 4 minus x squared minus y squared minus z squared. So here we've interchanged basically the y and the z. So what we get here is we get a hemisphere over in the y direction. So like this. Radius 2. Oops. And of course, if we flip this and did something like, say, y equals negative square root of 4 minus x squared minus z squared, we get a very similar picture. But in this case, the hemisphere would be over on the left-hand side. It would be over here. Again, extending to 2, negative 2, 2 up here, negative 2 here, and negative 2 over here. Because the y is the negative version. So all of these are hemispheres. So watch out for the difference between these, right? So again, just to re-emphasize, to put these last few examples together, it's the difference between these things that look very similar. And again, like I said, when you write them all side by side, it's especially easy to get confused. I mean, you'll do so many of these that eventually they'll become second nature and you won't get confused, really, unless you're not doing any homework. But if you're doing these problems regularly, you know, within a week or so, you'll know them. So again, the first one, paraboloid. Second one, cone. Third one, hemisphere. But all of them are fairly similar. So however you need to remember them that way. So let me keep going with just a few more examples that I'm not going to flesh them out so much, but we'll do sort of examples of them just so we see. Some of them will be familiar, some of them won't. Let me clear the screen off and do a bunch more. So I'll do one that may not seem familiar to you, but you've done it, which is why we don't need to do that many. Let's say xy equals 8 minus 2x minus y. So this is the same as z equals 8 minus 2x minus y. And some of you may see now that if you move everything to one side, well, everything except the 8, this should be familiar. This is a plane. So you may need to go back to 11.6 to look at these, if that's a bit rusty, which is understandable. But this is the kind of plane that we drew by drawing a triangular piece. We found the intercepts. So for example, when y and z are 0, x is 2, or x is 4, when x and z are 0, y is 8. And when x and y are 0, z is 8. So when we drew this as a plane, we do this little triangle. And again, I made this comment before, but it's worth thinking again, is this triangle doesn't end. It's not really a triangle, right? It's really a plane that's cutting through all the axes. And so this extends forever. But it's familiar. That's the key. All right, we'll do a few more. Let's do another plane. Let's actually make a good point about something. Something like f of xy equals, say, 10 minus y. So you might say, like, well, where's the x? Okay. So this is the same as z equals 10 minus y, which is the same as y plus z equals 10. And this is one of those planes that extends in the x direction, because x could be anything. And so what we get in this case is if I find the y and z intercepts, those are both 10. I'll connect those, and then this extends in the x direction, both forward and back. And again, you might need to look back at 11.6 to remind yourself about these, and that's fine, right? But the point is, again, it's a familiar one. And this extends left and right, extends like up and left and low and right. It's a plane that extends forever and ever and ever. A couple more. Again, a little bit esoteric. What if we had like z equals x squared? So then you might say to yourself, well, where's the y? So, just like the plane we just did, we're going to plot z equals x squared without y first. Then since y is missing, y is anything. So what we'll do is we extend it in the y direction. Right? So it can be helpful to draw like a little side picture here. So in other words, this equation, if you didn't have a y-axis, if you had just, I should do this a bit bigger. If you had no y-axis, you would do something like this. Have an x and a z, and you would draw a picture, and it would be like, use different color, something like, it'd be a parabola. That's y, that's z equals x squared. Now, if you move to 3 dimensions, that sort of aquamarine, whatever you want to call it, picture that we just drew above, that one, it's a parabola in the xz direction. So that's this way. So these I think that's a slightly different color. That's all right. Those are identical. All right, it's a bit hard to see, but they're identical. Then what we do is we extend this in the y direction, because y could be anything. So you get, looks a bit like a half pipe if you know how to skate. That's the shape, right? Now this has an actual name. This is a parabolic sheet, for obvious reasons, because it's parabolic, but it's like a sheet, like a bed sheet or a sheet of paper or something like that. And of course you can take a sheet of paper and you can bend it to emulate what this will look like. But the key to see is z equals x squared. Without y, it's just a parabola. With y, it extends in the y direction. Y could be anything, so it extends to the left and the right forever. And you could do the same, for example, if you did something like, say, y equals x squared. Now, this is sort of sneaky because you might look at y equals x squared and you might say, well, that's just a parabola. That's a pre-calc problem. So the response is like, it depends on the context, right? If you're in pre-calc, if you're in 2D, like really it's just this, bam, parabola. But in 3D, then we gain that third dimension. So again, let me draw 2 pictures here. The y equals x squared, right? That goes like this. That's this picture up here, really, if I did it like this. Right, because we've got the x-axis and the y-axis. So up here, this sort of wraps around the y-axis. So down in the picture below, it wraps around the y-axis. Then we extend it in the z direction. So we get another parabolic sheet, like that. And it goes, just keep in mind, it goes up and down forever, and it opens out to the right forever and ever. It doesn't stop, but typically we just draw a piece of it because otherwise it becomes an unreasonable thing to draw. So these are a bunch of different planes, parabolic sheets. So a couple more I want to do. Let me clear the screen off because I don't want to jam in the corner, but they're pretty simple. They're somewhat familiar. So something like, let's do, it'll remind you of something familiar. Actually, let me change it a little bit and make it a z squared over 9 equals 1. So you might look at this and you might say like, well, if the 4 and the 9 were not there, it was just x squared plus y squared plus z squared equals 1, then you've got a sphere. So what do these do, right? So these numbers that we've got, let me circle them. They change it from a sphere to like a three-dimensional ellipse, which has a name. These turn a sphere into what's called an ellipsoid. So we can graph that simply by finding the intercepts. Let me be pretty precise about this, right? So for example, when y and z are 0, we get x squared over 4 equals 1, so x is plus or minus 2. When x and z are 0, we get y squared equals 1, so y is plus or minus 1. And when x and y are 0, we get z squared over 9 is 1, so z is plus or minus 3. So the easiest way to draw this, I think, for me at least, is to plot those intercepts and then just do the best you can do about filling in like an egg shape. It's not easy to do, in fact. So the z's will be up and down at 3, pretty far apart. The y's are at 1, those are really close. And the x's are at 2's. So what I'll sometimes do for this is I'll draw like an equator in the xy plane. And then I'll do my best to sort of fill up the top and the bottom. Again, it's not going to be perfect. Doesn't have to be. We can label it. We can label the intercepts if it helps us sort of get a grip on what we just drew. But again, the key is to draw something reasonable that you understand, that you can work with. It's, you know, we're really not going to be grading on pictures, and if we do, it's very generous. So really, it's like, you know, later on we'll be drawing these pictures and then needing to do something with them. And so it's the drawing a picture that's sufficient for you to do something with them that's key. All right, so last couple. So this will remind you of when we just did something like this. You might look at this, you might be like, well, that's a circle. So here's the key. In 2D, it's a circle. In 3D, z could be anything. So what happens is it's a circle that stretches in the z direction, which you can probably see becomes a cylinder. So this, as a circle, x squared plus y squared equals 9 would just be a circle in the xy plane. It would be like this, radius 3. But allowing z to be anything moves it up and down. Now keep in mind this cylinder is hollow. Right, it's not a cylinder like a filled-in cylinder. It's not x squared plus y squared less than or equal to 9. This is I'll use the word hollow, but people typically won't. I'll put it in parentheses. It's a hollow cylinder. Extends forever in the z direction, up and down. And then last, I'll do one more cylinder. I'll just switch some variables around. Say like x squared plus z squared equals, say, 4. So in this case, it's the y that's missing. So it's the y that can be anything. And so this cylinder will stretch in the y direction. And this has radius 2, so it goes to plus or minus 2 here. It's the x-axis at 2, goes forever to the left and the right. That's a negative 2 down there. So I'm going to stop there for these pictures. This is the end of 13.1A. 13.1B will be a little bit shorter, but I want to keep it separate because this was enough. But what I would suggest is like, look at these examples and look at sort of versions of these examples, right? The book has a few other esoteric things that are hard to draw, but primarily we'll focus on these types of things. So look at these examples and think about variations of them. Like, how could you make an ellipsoid do what you want? How could you have a paraboloid positioned where you want and opening in a direction that you want? What if you want a cone that comes forward? What if you want a cone that goes to the left? How can you do that? So look at these equations and look at common themes on these equations, and that will be sufficient. So that's the end of 13.1A.